In this video, we're going to continue finding the area under a curve using this method of putting a bunch of rectangles under the curve, calculating their areas, adding up all the areas to get an approximation. We're going to see some definitions and some new symbols. So we're moving in, not very quickly, but we're working up to getting the calculus of how you calculate the area under a curve. We're going to be using the operation of integration, and that symbol for the integral is that elongated S. This is a definite integral, and when we learn how to do that operation, that is what will give us the area under the curve. But we're going to ease into that the long way around. It turns out that that definite integral is nothing more than the limit as n approaches infinity of the sum of the areas of all the rectangles. So A of I is the area of the ith rectangle, so maybe you're up to rectangle number 10 and you calculate its area. Then you go on to rectangle number 11 and you calculate its area. That symbol is sigma, that's a capital S, a Greek capital S, says add them all up. So as you calculate each area, you add it into your running total. And then you have an index. I is equal from 1 to n, and that's like a little counter. So the counter starts at 1, so you're starting at the first rectangle, and you're continuing up to count as many rectangles as you need. So whatever you've chosen n to be. Just a little bit more about that sigma notation. Again, I is called the index of summation. You can think of it as a counter. And here a sub I is the ith term of the sum. So you would be adding a sub 1 plus a sub 2 plus a sub 3 and so on and so forth until you get up to the last term. Hopefully you've seen this notation in your pre-calc class. You may have done a little bit on series and sequences. There are some handy summation formulas. The first formula is one that, actually you should remember that one. The others you can just refer back. You don't need to memorize those, but just remember that there are formulas. So the first formula says, well, if you add up a constant n number of times, then you just multiply n times that constant to get the sum. Formula number 2 is if you want to add up the first n numbers, 1 plus 2 plus 3 plus 4, etc. There's a shortcut formula for that, n times n plus 1 all over 2. If you want to add up the squares of the first n numbers, 1 squared plus 2 squared plus 3 squared and so on. And formula 4, what if you want to add up the cubes of the first n numbers? So 1 cubed plus 2 cubed plus 3 cubed and so on. There's a handy dandy little formula for that. All right, so then we come to the formal definition of area under a curve, which turns out to be the limit. So this is a limit definition. The limit as n approaches infinity. So as the number of rectangles becomes arbitrarily large, you calculate the area of each rectangle. So f of x sub I would give you the height of the rectangle, and delta x stands for the width of the rectangle. And remember, we're setting it up so that the width is equal. The width of all the rectangles is equal. So if you take the length of the interval that you're looking at and divide by the number of rectangles that you want, that would give you the width of each rectangle. So in that first formula, a is equal to the limit of n approaches infinity of capital R sub n. Your textbook just uses that R sub n, and then in the second formula, the L sub n, to mean which method you're using to set up your rectangles. Are you using the right-hand corner or the left-hand corner? And then there's a little bit of a different notation if you're picking a place that is not the left-hand corner or right-hand corner to figure out the height of your rectangle. In that case, you use this notation star. So x star means it's somewhere in the interval of that rectangle. And just to get a visual on that, the very first graph there on your left shows rectangles set up with left-hand endpoints, so it's the left-hand endpoint that's going to dictate how you figure out the height of each rectangle. In the middle, it shows a visual of using the right-hand endpoint, so it's the right-hand endpoint that's going to dictate the height of each rectangle. And then the third one is actually showing you a midpoint, but it doesn't, again, have to be the midpoint. It could be any point on the rectangle, but in this case, you're using the midpoint of the rectangle to determine the height of each rectangle. And again, the widths are always the same. Well, we'll go on after this and do some examples.